Okay. So, quick few announcements before we get started. The first recitation for the class will be tomorrow evening at 5. I forget the room number, but it's on our website, like all information is. And these are optional recitation sections hosted by the teaching assistants. But even though they're optional, I strongly encourage you to attend those if you want to go into get some more help with some of the material. And tomorrow's recitation in particular is going to cover material on probability and also decision trees. So it's very relevant to the homework. Oh, homework. That was my second announcement. As you noticed in your email box on Friday, the first homework is out. And I'll tell you, I think the homework is pretty reasonable. There's one question on there about Poisson distributions, which will test your true recall on that old probability course you took a while ago. But the other two questions I think are pretty straightforward. If you need some help with the Poisson distribution question, the recitation is the perfect place to come. Okay? Question?
So, you said somewhere that you want 2 copies of the homework. Do you want the homework in LaTeX, or can it be scanned in, or is there a particular format that you want?
TAs want to answer that. Do you want it said you want 2 copies of the homework. That's hard copy or electronic?
Not 2 copies, but don't put them together because TA needs to get 3 copies of grade. I mean, that's separate questions to different TAs.
I see. So the point is different TAs are going to grade different questions. You can figure out which TA by looking at the TA name next to the question. And so the thought is don't stick it all into one thing and submit it. Just submit it in pieces so that it can easily be split up among the TAs. Okay? Other questions? Okay, then today is really the one and only review session that we're going to have in class. I think I've taught this course a couple times, and I found it really is useful to have a session that zooms through at very rapid speed all the things that you might have seen in earlier courses about probability, and that focuses in on the material most relevant to this course. But you will see during the course that understanding probability, random variables, distributions, entropy, mutual information, these different notions about probability distributions is central to passing the course. So it's worth taking a day. And I apologize in advance for those of you who are already experts in this material. You can just kind of use this as a way of calibrating your understanding to the terminology and notation that we're going to use. But for the rest of you, I think it'll be useful to zoom through this. Okay, so we started looking at the end of last lecture, we started actually looking at random variables, probability distributions, and so forth. Just to refresh your memory, it's handy to visualize these probabilities in terms of the Venn diagram that represents the event space. Then we can think of, for example, a Boolean random variable like A or B as defining some subset of the event space for which that variable has the value true. So if this is the space of all events, like each student in the class could be a random event. If I point to a random student, that's an experiment. And I could get the value of random variable A as this student female, for example, or bald, for example. There at the intersection would be, of course, students who are both female and bald, both A and B. And you can see that's a smaller probability than any one of those variables individually being true, at least for the particular way I've drawn those. Okay? All right, so with that in mind, maybe one obviously important notion is conditional probability, which is defined this way. If we're interested in the probability that A is true, given that B is true, well, that's just the probability that A and B are both true divided by the probability of B. That's the definition of conditional probability. And one way to think about that here is this would be the region in which both A and B are true. And if we're interested in the probability of A given that we know B is true, the probability of A being true given that we know B is true, well, that would just be the fraction of all of the probability mass associated with B being true, and the subset, the fractional part of that, for which A is also true. Right? So it's sort of the ratio of this hashed off area to the entire area of B. So that would be the probability that A would be true given that B is true. And if you think of it that way, then you could even just write down this formula if you happen to forget it, because, of course, that hashed off area is just the probability that both A and B are true, and the denominator is just the entire probability mass associated with B being true. Okay, so I find that a handy convenience. And for conditional probabilities, since we define them this way, there's a handy corollary to keep in mind, which is that, well, if we multiply both sides of this definition by P of B, then we get this expression. The numerator, P of A and B, is just this left side times P of B. That's called the chain rule. If you think about it, what it means, what it's saying is the probability that A and B are true is just the probability that A is true given B times the probability of B. And again, it just follows from our definition. And this is called the chain rule. In fact, it generalizes to arbitrary conjunctions of arbitrary numbers of random variables. So, for example, we could easily prove this more general version of the chain rule from this one, because notice this part here is just P of A and B. Right? That's what this equation here is saying. So by the chain rule, this part equals P of A and B, and then if we substitute that, then we just have another instantiation of this, where instead of having A and B, we now have C and those. This chain rule is a very handy thing. We'll see that, in fact, by the end of this very class, we'll be talking about joint probability distributions over large collections of variables. And often we'll be interested in factoring that joint distribution into a set of terms that get multiplied together so that we can work with them individually. And the chain rule is actually one of our favorite tools for doing that. Okay. Independent events. So we'll define two events or random variables. We'll say they're independent if the probability of their conjunction is just the product of their individual probabilities. So let's see. Well, in other words, what this is saying is that A doesn't really tell us anything about B. The probability that you're here, well, no, the probability that that there are an even number of students in the class is independent of the probability of whether, when I flip this tack in the air, it's coming up with a point up or the point down. So those are two different events, but knowing whether there's an odd or even number of students in this room won't really tell me anything to help me gauge the probability of this other thing. So those are two independent random variables. Okay, now think about our Venn diagram for a moment. What would it look like if I wanted to draw the regions for two random variables A and B that were independent? What would that look like? Well, here's how I can do it. I'll say this is A, that region. And of course, this region then is not A. And I'll say this is B. Meaning, when I say this is B, I mean the entire area below this double line. That's a thick line, sorry. That's B. Okay, so now what do I mean by that? Well, this is my Venn diagram again. So the probability of A, if I think of this as just a region, a square with unit area, so that's the entire event space with probability 1, then if I draw this region to be A, well then this here is, actually this point is the probability that A is true. Right? It's that fraction of the area. And what's the probability that B is true? Well, that's this. Right? And where's the probability that A and B? Well, that's, of course, here. But why does this make these independent? Oh, well, because this is our definition. The probability that A and B, where's that? Well, that's just here. Equals the probability of B alone times the probability of A alone. So in a way, what I've done here is I've just chosen a way to draw my Venn diagram so that A and B are really kind of independent. I can put that B at any, I can put the B line at any height, I can put the A line at any width, and they're independent. Knowing whether B is true or false doesn't really tell me anything about A. Right? In other words, before I know about B, the probability of A is just this, and probability of A given B, oh, what's that? We just discussed it, right? Probability of A given B is the probability of their conjunction over the probability of B. And in this case, that just equals, whoops, what am I doing? I got lost. So just don't worry about that. Actually, what I was going to try to say was that the probability of A given B is just the probability of A. Knowing B doesn't tell us anything about it. That's where I was headed. Okay? All right, so we just did that. So now, many of you know about Bayes' rule. And it's this widely used expression that we will be using a lot in the course. And an easy way to derive it is just to write down two different expressions for the probability of A and B. For example, given what we know about the chain rule, or just kind of reading it off this diagram equivalently. So for example, how could I write, one way I could write probability of A and B, which of course is this region in the middle, is by the chain rule, that's just the probability of A given B times the probability of B. A different way I could write it is to say, well, it's the probability of B given A times the probability of A. I could apply the chain rule either way. You see, it makes sense if I take, for example, this one on the left here, then it's just the probability of A multiplied by the fraction of cases of B in which B will be true given A, which will give me this region. Okay, so if I write down those two equivalent expressions for the chain rule, for the conjunction in terms of the chain rule, then what if I just divide through by, let's say, P of B? Let's divide through by that. Then I'm going to get P of A given B equals, oh, let's use this one on the left. P of B given A times P of A, all divided by P of B. That is Bayes' rule. So, in fact, it follows very directly from very simple analysis here. And it's incredibly important because what it tells us is how we can compute conditional probabilities in terms of other terms that might be more accessible to us. And in fact, we'll see this week that we'll be able to train machine learning programs that represent, instead of learning functions like the decision tree did, instead of learning deterministic functions like we talked about last week, function from x to y, we'll generalize that to, why don't we learn conditional distributions? Instead of a deterministic function from x to y, let's just learn the conditional probability of y given x. And then we'll find this week that the probability of y given x we can express in terms of these kind of other terms and train very useful classifiers using Bayes' rule. So Bayes' rule is a biggie. So big that we've put his picture on the slide. The Reverend Bayes, 1763, bless his soul, he's a reverend. And I like this quote. Because he kind of got it, he kind of nailed it. He said, what is likely to be hereafter necessary to be considered by any that would give a clear account of the strength of analogical or inductive reasoning. He was right. He really got it. Okay, so that's Bayes' rule. And a little bit of terminology. You'll often hear people talk about the prior distribution or the prior. They're talking about P of A, this thing. And you'll also hear people talk about the posterior distribution, and they're talking about this thing. And often this is because B will often be evidence of some type. And in fact, we might have some prior hypothesis. For example, any of you could have the flu right now. I'm going to guess that only about 5% of people have the flu. So I'd say a random one of you who I pick, there's a prior probability 0.05 that you have the flu. But now if I see that you just coughed, I've got some evidence. I might want to change the probability that you have the flu given that you just coughed. And I can apply Bayes' rule to do that. So for that reason, we often talk about this as a prior, the prior that you had the flu, and the posterior probability, for example, the posterior that you have the flu, given the evidence that you just coughed. There are a couple other forms of Bayes' rule, but they're all equivalent. You don't have to memorize these because you know enough about probability to derive them from the form that we already said, because this is just P of B, which is what we wrote down the previous time. And you see all we've done is we've just written P of B by expanding it out in terms of all the possibilities that A could take on. So if A is a Boolean variable also, then it's either true or false. And so the probability of B is just the probability of B given A being true times the prior that A is true, plus the probability of B given that A is not true times the prior of A not being true. And this second expression is just to point out that the things that we condition on don't have to be single variables. We can put conjunctions or expressions in there. Okay, so let's go through a very simple example. As I mentioned, I think about 5% of people have flu. Let's make that the variable A. You have the flu. You just coughed is another Boolean variable. Could be true or false. I heard somebody cough. So we'll pick you as our case. You just coughed. And now if we're interested in the probability that you have the flu, that's our variable A, given that you just coughed, that's our variable B, then we can apply Bayes' rule here. But to do that, we need these different terms. So I'm going to say the prior probability of the flu is 0.05. Seems kind of reasonable. The probability that you cough, given that you have the flu, let's say is 80%, 0.8. And we also need this other funny term, the probability that you cough, given that you do not have the flu. And I'm going to guess people cough for random reasons at different times, so I'm going to say 0.2. Okay. So now what is this according to Bayes' rule? Well, we can just write it down. It's the, so you can help me read this off. The probability of B given A is 0.8. Probability of A is 0.05. That's the numerator. The denominator is, oh, well, this thing is just the same as the numerator. Plus, what? The probability that you cough given that you don't have the flu. Oh, we knew that. 0.2 times the probability, the a priori probability that A is false. What's that? Right, 0.95, because P of not A, of course, is just 1 minus P of A. Okay, so this is, what's that give me? 0.4 over 0.4 plus 0.19, which is 0.4 over 0.59, which is darn close to 0.67. It's about 2/3. Okay, so a priori you only had a probability of 0.05 of having the flu, but since you coughed, oh, did I do bad arithmetic? Oh, 0.04. Thank you. Wow, okay. Wait a minute. Gotta love technology. Pretend that never happened. Thank you. 0.04. Oh, wow, this is big. 0.04 plus, I got that other one right, though, right? 0.19. Wow, okay, so good news for those of you who are coughing. What's that approximately? approximately 0.18. Good. So coughing is not a good sign. It did increase your probability from the prior of 0.05 up to 0.18, but fortunately it's not as bad as I thought it was when I made the arithmetic error. Okay. If you cough twice, I don't know what we're going to do about that. I guess then we'd have to decide whether those two coughs were independent pieces of evidence. But we won't go there right now. Okay, Bayes' rule. All right, now what does all this have to do with function approximation? Well, it's basically what I said before. Before we were interested in learning functions from some x to some y. For example, in the decision tree lecture, we talked about x being some vector of different random variables, like is it humid outside, what's the temperature, and so forth. And we tried to learn a function from that to yes or no, this Boolean variable y, would the person play tennis? But it's just as good, really, maybe even some would argue better. We could learn this instead. So we could learn that deterministic function, but really a lot of the world is not characterized by a deterministic function. And so we're interested in probability distributions on y given an x. And so that's what it has to do with function approximation. Learning p of y given x is going to be just as important a goal for us as learning these functions. In fact, we'll kind of talk of them as roughly equivalent ideas. It's just a question of whether we want to commit to it being a deterministic function or a non-deterministic function where there's a probability distribution over different possible values of y given an x. Okay. All right, so let's move on and look at the idea of a joint distribution. So if we're going to be dealing with learning p of y given x's, where our x's are actually vectors of variables, like the temperature of the day and the humidity of the day and the outlook and the windiness, then in general we're going to have several variables and we're interested in the joint probability distribution over those variables. What do I mean by the joint distribution? Simply put, I mean if I have a collection of variables like A, B, C in this case, I'm interested in the probability for any assignment, joint assignment, I can make to those variables. If A, B, and C are Boolean variables, then I could talk about the probability of, I guess there'll be 8 possibilities for 3 Boolean variables. I could have B equals true, A equals false, and C equals false. And in this Venn diagram, the probability of that assignment would be 0.1. So a joint distribution just means I can represent it here or equivalently this table. It just means that I have a probability assigned to every possible joint assignment of my random variables. Okay. And it's very simple to make one of these. It's not difficult at all. We simply make a truth table listing all the possible assignments of our random variables. If I have m random variables and they're Boolean, then of course I'll have 2 to the m rows in that table. I will, for each of those configurations, to define a joint distribution, I have to write down the probability that the world will exhibit that particular joint assignment. And that's what the rightmost column is. And then, given that I believe in the axioms of probability, I have to make sure that the column off on the right here of all those probabilities, of course, has to sum to 1. I'm in a world where all of those, every random experiment I do, I get in a joint assignment for those variables, and they're going to take on some value, so the probability has to sum to 1. That's a joint distribution. Very simple idea. incredibly valuable idea because given the joint distribution over a collection of random variables, you can compute the answer to any question you like about marginal distributions. That means probabilities of just one of those variables taking on a particular value, or conditional probabilities. Any conditional probability I give you, you can compute from the joint distribution. So it's kind of the what's the word? It's the ground. It's the foundation from which you can calculate any other conditional probability or marginal probability that you need. So if you know the joint distribution, you don't need any other information. You might need some computing time, depending on what you want to do with it, but you don't need any more information. Okay, so now let's look at an example. This is some data that my friend Andrew Moore dug up. It was an employment kind of demographic database, and it has 3 variables describing people. The variables are the gender, the number of hours they work. These are all Boolean variables in this version of the data. So the gender might be female or male. Number of hours worked might be more than 40.5 or less than or equal to 40.5. And then their wealth, well, they could be rich or they could be poor. So those are 3 random variables. They came out of a real database describing people. And the red numbers off on the right are the probabilities for each of those joint assignments. Okay. And just to be clear, these are all cases where gender equals female, and these are all cases where gender equals male. So like this last row in the table, gender equals male, hours worked equals more than 40.5, wealth equals rich, and that happens in 0.10 of the cases. Okay, so this is a joint probability distribution over these 3 random variables, where the event space is what? Set of people. And to sample those random variables, what do? We pick a random person out of the database. And now we get a random draw, a joint assignment to these 3 variables. Are those variables independent? Not necessarily. We might find it more likely that when we draw a random person, that we might find it, for example, more likely that if they're wealthy, then they also work more than 40.5 hours a week. And we might find it much less likely that if they're wealthy, they work less than that. Because there's a cause-effect question there. So they're not necessarily independent random variables. They could be information about one of those random variables might give us information about others. But this is just the joint distribution, how often each of those different configurations occur. So given that, we can now ask, essentially, for any expression that we like, E, we can ask, well, what's the probability of that happening? What's the probability that somebody will be rich and work less than 40 hours a week? We could ask. How would we answer it? We just add together the rows in the table that satisfy the condition I just described. And and then we add together the probabilities for each of those rows, and that'll tell us how often, out of the total probability mass of 1, that particular event holds. So that's the beauty of the joint distribution. So let's look at a couple simple cases. We could ask, what's the probability that somebody will be both poor and male? Well, there are 2 rows in our database, 2 rows in our joint distribution for which this is satisfied. The 2 circled ones here. If I add together the probabilities of those 2, then I know the probability that a random draw of the values of this joint distribution will result in in wealth equals poor and gender equals male. It's that simple. Okay. We could ask, what's the probability of being poor? Well, then we have our 2 rows from before plus 2 more rows. There are 4 rows in this joint distribution table that satisfy that, and we add together the numbers, we see the probability of being poor. In general, we can do not just probabilities of particular events, but we can do conditional distribution questions too. What's the probability of being male given that somebody is poor? Well, that's just the probability of the conjunction over the probability of the thing we're conditioning on. That, remember, was our definition of conditional probability from a moment ago. And we already know how to get these 2 things. The probability of E2 is just summing up all the rows that match E2, and similarly, the probability of the conjunction, we just sum up the rows that do that. So for the, in this case, the denominator, the probability, it would be the probability of being poor. That'll be these 4 rows. That gives us the 0.76. The numerator is just only 2 of those rows, the ones for which somebody is both poor and male. And so by taking the ratio of those 2 events, we now have our conditional probability of male given poor. Good? All right. Good. So you see the joint distribution is really that, like, if you ever get confused and you're in the middle of some kind of probability quandary, just go back to thinking about the joint distribution and then work your way up from that. And you can always do it if you know the joint distribution. All right. So now, well, this slide really just kind of, in a funny way, says it again. But I just want to drive home the point that from the joint distribution, we can calculate anything. And so in a way, what that implies is that if we can learn the joint distribution from some data, we can get P of y given x. That's all we need, and we're done. As long as we have a sufficient computational power to do the collection of those rows in the table and sum them together. And if it's a sufficiently small table, that's trivial. If it's a big table, it could be an issue. But so, for example, I might take the same data set from which this joint distribution was estimated, and from that data set, I might be interested in learning the target function that predicts whether you're wealthy or not based on your gender and the number of hours you work. Predict W, wealth, from gender, G, and hours worked, H. Equivalently, I'm interested in this conditional distribution on wealth, given your gender and number of hours worked. And, well, it's easy. We just went through that. So if these are actually the probabilities of those, the joint distribution, then you can figure this out easily, right? It will just be what? This will be what? This will be, well, for the numerator, how many rows will I add to get the numerator for this particular thing if I want to know the probability of being rich, given that you're female and you work less than 40 hours? How many rows will I sum together in the numerator here? 1. 1, right. It'll be this one. And how many rows will I sum together? Whoops. Yeah, how many rows will I sum together in the denominator? 2. It'll be this one plus female and less than this one. Look, it's looking bad for the probability of being rich if you're female and work less than 40 hours. Okay. Inexact arithmetic reveals. But so if we're interested in learning some target function or some conditional distribution of y given x, such as the conditional distribution on wealth given gender and hours worked, then all we can reduce the learning task to the task of learning the joint distribution. And then anytime we want to know for any given new example that we have to guess whether they're rich or poor, we just put in the attributes of the new person. We calculate the probability that they're wealthy. We also calculate the probability they're not wealthy. Oh, that's easy, right? That's just 1 minus this, because those two things have to sum to 1. And we're done. So we can reduce the problem of learning this conditional distribution to the problem of learning the joint distribution. It's sounding simpler and simpler. Okay, so that's it. And this is kind of why, if you're wondering why are we going through this probability stuff, this is why. It's really central. It's another way of looking at function approximation. Okay, so now if the only thing we have to do is learn the joint distribution, that sounds pretty easy. It was easy in this case. We had a big database. We just counted, actually what Andrew did there is those things that he was calling probabilities in red, they were just a fraction of people in the database who satisfied the constraint on that particular row. So that was pretty easy. That's good. We would have a very short course if that was actually the end of the story, so it's not. The reason it's not the end of the story is because that table we just looked at was very simple. Very simple table. It only had 3 Boolean variables. Of course, if we have n Boolean variables, we'll have 2 to the n rows in that table, right? And so if I had a more realistic database where maybe my people were described by, 40 variables, that's not good. That's like 1,000,000 times 1,000,000. So that's a big number. 2 to the 40 will give me 1,000,000,000, what's that? Trillion. Trillion rows in the table if I have 40 variables. 2 to the 40th is roughly 1,000,000,000,000. So, well, that's okay. Computers can handle that. It's really not a problem. Computers have big memories. We could, my laptop can handle that. My laptop can store 1,000,000,000,000 numbers. So that's not so horrible. Here's the problem. We'd need at least 1,000,000,000,000 people in our database to make sure that we had at least one person who satisfied every row. We have 1,000,000,000,000 rows. We can't even, they're going to be, if we have 1,000,000,000,000 rows and 1,000,000 people in our database, they're going to be a lot of rows where no person in the database lives in that row, so to speak. And so we won't really know how to estimate the probability because we won't have any data about that particular combination of variables. So one reason that we're not done, I'll give away the answer. We're not done. Part of the reason is because in realistic learning problems, we have not 2 or 3 variables, but often dozens or hundreds. In fact, in our research, we routinely work with problems where we have tens of thousands of variables, sometimes hundreds of thousands of variables, and try to learn to predict things from these very large high-dimensional vectors. And so in those cases, it's really not realistic to learn every term in the joint distribution, at least in that kind of rote way that we described it in the previous slide. So what I want to do now is move on to how do we estimate parameters in these joint distributions. And in general, when we try to characterize probability distributions, how do we estimate parameters for those distributions? And you can think of here, these are parameters in this joint distribution. To define the joint distribution, we had to write down 1, 2, 3, 4, 5, 6, 7, 8 numbers. Once we define those 8 numbers, then the joint distribution is defined. Do I really need 8? I could just learn 7 numbers, right? Because we know they have to sum to 1. Okay, 7 numbers. 2 to the n minus 1 numbers I'm going to need as parameters. Those numbers I'll call parameters that define this joint distribution. And so now an obvious question is, given a data set, how should we use that data to estimate the value of these parameters? So that's what I want to talk about next. And to make this the simplest example possible, let's talk about estimating just one parameter, which is the probability that a thumbtack, I didn't actually set this up. Somebody just left me this thumbtack through good fortune. But we're going to say I'm going to define a random variable, which is the probability that when I do that, it ends up with a point down. It didn't this time. Okay, and I could repeat that experiment, obviously, a number of times. And each time we'd be sampling that Boolean random variable, point down or not. And I might be interested in the probability of a random draw of that random variable having the value 1 point down or the value 0 point up. So this slide, which I borrowed from my friend Carlos Guestrin, tells this tale in some kind of mysterious story that involves a billionaire in the suburbs of Seattle who has a thumbtack like this, and he flips it and he wants to know what's the probability, given these experimental outcomes in 5 different random flips, what's the probability that the thumbtack the next time it's flipped will end up point up versus point down. So what's the probability to end up point up? Thank you. 0.6. So the consensus estimate here is 0.6. Why? Well, that's the frequency with which it's done point ups in the past. What else could we use? So it turns out there are a couple things we could use to answer this question, and let's to estimate this parameter, and let's look at that. So one way to think about that random variable is a Boolean random variable. We could say it follows a Bernoulli distribution. By that I simply mean there's some probability theta that it will end up a heads, and there's some other probability 1 minus theta that it will end up tails. And of course we don't know theta, but we've got some data, and our job is to estimate the parameter theta from that data. Okay, and so what I could say is I've got, when I run those 5 experiments shown here, I actually have 5 different random variables. There's a random variable. there's another one. Each of these are Boolean random variables. Each of them follows the same identical distribution. That is, with probability theta, I don't know theta, but with probability theta, it's going to have point up, and with probability 1 minus theta, it's going to have point down. And so if I ask you, what's the probability of this entire data set? So D is going to be now this whole set of flips. What's the probability that that would occur? You can't actually answer that question without making one more assumption, right? Not only do you want to assume they're identically distributed, but you want to assume they're independent events. So I'll grant you that. Let's say they're independent, identically distributed 5 random variables here, x1, x2, up to x5. They're all independent. And so now, what's the probability that I would see 1, 1, 0, 1, 0, given that the probability of a single heads is theta? Yeah, it's just the product of the individual probabilities because they're independent. And so, in fact, we could say, well, the probability of this first one, that's theta. It was heads. The second one, that's also was probability theta. This third one, well, that's 1 minus theta because that turned out tails. That's the probability of the data. You know, I'm going to rate this given theta. The system, oh, that's another 1, so that was theta. That's a 0. The probability of that was 1 minus theta. And so the probability of this entire data set, given theta as the parameter, is just the product of those things. Why the product? Because they're independent events. And remember, we said what it meant to be independent was the probability of the conjunction is just the product of the probabilities of the independent events. Okay? All right, so there's the probability of this particular data set that has these 5 observations, 5 pieces of evidence. Let me rewrite that. Let me say that there are alpha t tails, outcomes, and alpha h heads. Okay, then I can rewrite this very easily as just, that's theta times the number of times it was heads, times 1 minus theta, times the number of times it was tails, right? I'm just rewriting that expression. Right? It's just going to be the product of these terms. There will be alpha h of them that will be thetas, and alpha t of them will be 1 minus thetas. So there's my probability of the data given that I observe alpha h heads and I observe alpha t tails. So we can, it turns out alpha t and alpha h are sufficient statistics. They're all we need to know about this particular experiment in order to get our estimate of theta, mostly because they're IID events. Alpha h and alpha t you can also think of as random variables, if you like, the same way that we thought of the outcome of each experiment as a random variable. And alpha h and alpha t will follow, well, what's called a binomial. Those counts will follow what's called a binomial distribution. But here's essentially what we just calculated above. And what's important is this is the probability of the data given the unknown to us theta parameter. Okay, so now the question is, how do we want to estimate theta? What's the criterion? What's the basis on which you'd like to pick a theta? And we're going to talk about two ways of doing that. And the first is called maximum likelihood estimation. What does that mean? That's a term with way too many syllables for a simple idea. The simple idea is we want to pick the theta that maximizes this probability of the experimental outcome. Given that, what do you think is more likely? Do you think theta, suppose I give you two choices. Theta could have been, here are your two choices. Theta could be 0.6 or 0.1. What do you think is more likely? I think 0.6, because 0.6 of those outcomes were heads. I'm not sure. It could possibly be in 0.1. It could be that the probability of a 1 is 0.1 and not 0.6. And it's still possible that we could have gotten this sequence of experimental outcomes. It's just not very likely. And so what I want is I want the theta that's going to, in particular when I say maximum likelihood, I want the theta that maximizes this quantity. So my maximum likelihood estimate is just going to be the argmax over all possible values of theta of the probability of the data given theta. I just pick the theta that maximizes that thing. And you see why that's reasonable? I mean, it's sort of like you've got to pick some theta. You might as well pick one that makes the stuff you see in the world probable instead of improbable. Okay. All right, so to put this kind of precisely and generally, so we observed a set of heads and tails. We assume these alpha h and alpha t follow a binomial distribution, which is just that expression we saw. And learning theta is an optimization problem, which we're going to define when we talk about maximum likelihood estimation. We're going to define that as picking the theta that makes the observed data the most probable out of all the thetas we could have picked. And of course, since it doesn't really matter if you're picking some function to optimize, to maximize, and we're trying to pick the theta that maximizes it, we can equally well pick the log of that function. It'll be maximized for the same value of theta. And as we'll see in a second, it's a little bit easier to work out the arithmetic if we make this second choice. So we like that in general. So this is often called the data likelihood. And this often called the log likelihood, for obvious reasons. Okay. All right, so, whoops. So to maximize this thing, if we decide we want to maximize the log of it, then that's just the log of this probability of the data of seeing alpha h heads and alpha t tails. The obvious way to maximize that is to take its derivative and set it to 0. If we have some function of theta, oops, that was an unfortunate choice. If we have some function of theta that looks like that with only one local optimum, and this is our theta, and this is f of theta, then a nice thing to do is to find where the derivative of f is 0, and that can be the maximum. Okay, so let's do that. Let's work out the arithmetic. It's actually not too hard. So again, here's our data likelihood. It was just that expression that you and I made up a minute ago, which multiplies together all those probabilities of those independent 5 events. And if we want to optimize that, first since we're interested in the log of this, we can rewrite this in a nice way. That's just alpha h times the log of theta plus alpha t times the log of 1 minus theta. Right? Okay, so now we want to set the derivative of that. We want to get the derivative of that with respect to what? Theta. Theta, right, because it's theta we're trying to find where that curve maximizes, where the slope with respect to theta is 0. So the derivative of that with respect to theta, of course, is just alpha h times the derivative with theta of log theta. Uh-oh, we're going to need to know what that is. Anybody remember from freshman calculus? I cheated and looked it up. Here's the hint. The derivative of the log of some variable with respect to that variable is just 1 over it. Whew, that's handy. Do not forget this. Okay, so now it's easy. That's just alpha h times 1 over theta plus alpha t times, chain rule stuff. Oops, I left out my log. I shouldn't have had this log here. That's it. Okay, so there's the chain rule. I can take the derivative of this thing, I'll just expand into its derivative with respect to 1 minus theta times the derivative of that with respect to theta. Chain rule. Again, freshman calculus. Okay, so then now we have this plus alpha t. The derivative of that is just minus 1. And the derivative here, again, is just another instance of this. So that's 1 over 1 minus theta. And I may as well copy this so we have the final version. Okay, so there's the derivative. And we just want to set that to 0 and solve for theta. Okay? So it's pretty straightforward. You can do the arithmetic to solve for theta. I won't do all the manipulations. But when you do, what you get is this very nice, simple expression. Interesting. So what this is telling us is our maximum likelihood estimate for theta, the theta makes the data the most probable, is just the fraction of times the coin turns up heads, which of course was what you intuited before we began all this math. But it's kind of refreshing to know that if we tried to be principled and come up with this maximum likelihood criterion, write down the assumptions IID, identically, independently distributed, independent, identically distributed random variables. Then when we work out the arithmetic, we get, in fact, a proof that the maximum likelihood estimate for theta, the one that makes the observed data most probable, is exactly the thing that you thought it would be. It's the fraction of times the coin turns up heads. So that's pretty good. Okay, maximum likelihood estimates. You'll see a lot of those through the course. And in many cases, we'll be interested in where theta is not just a single number, but where theta is a vector of parameters. Sometimes hundreds of thousands of parameters, and we're interested in the maximum likelihood estimate of that vector of parameters. But you'll be seeing this again and again, and you'll get a chance during some of the homeworks to derive your own maximum likelihood estimates for various things. Okay. So now this is pretty good, and so as we saw before, this was 3 out of 3 plus 2. 0.6 was our probability. This is the MLE estimate for theta, the maximum likelihood estimate for theta. It's 0.6. Okay, now there's one little subtlety here I'd like to raise, which is, what if you had a lot of spare time on your hands and you flip that coin, flip that thumbtack 1,000 times instead of 5 times, and you got suppose you flipped it only 500 times and you got that number. Okay, so if you flip the coin 500 times and you got this data, you would calculate by the same logic. The maximum likelihood estimate is 0.6. Which of those two estimates do you believe more? Second one, obviously. There's more data there. So one thing that's a little bit nerve-wracking about the maximum likelihood estimate is that it appears to not be influenced by how many times we flip that coin. Well, you have to take that with a grain of salt because, of course, I'm making these numbers up too. But in truth, what you would expect is that if you repeated the small experiment, the 5-flip experiment, several different times, you wouldn't expect to get the same maximum likelihood estimate every time you ran that experiment. You'd expect a lot of variance in your estimates, your maximum likelihood estimates for theta. Maybe someday you get 3 out of 5, 0.6. Sometimes you'd get 2 out of 5, 0.4. Sometimes you get 4 out of 5, 0.8. If you repeated this experiment many times, you'd of course also get some variation. But you wouldn't expect it to vary from 0.4 to 0.6 to 0.8. If you're flipping it 500 times, you'd expect the variance to be much smaller. Much more centered around 0.6, maybe down to 0.55 or something, but not down to 0.4 very often. So there's something here we'd like to wind into this that has to do with the amount of data that we have, and maybe also our prior expectations. If I did this with a coin, a penny instead of a tack, a penny for which you have pretty good intuitions a priori that it's about 50%. If the coin's bent, it might not be exactly 50%. But a priori, you have some expectation that the coin is probably 0.5. And so if this was that kind of a coin, you might want to build into this estimate your prior expectations about what you think theta probably is. It's probably close to 0.5 somewhere. Maybe not exactly 0.5, but close to 0.5. It's probably not 0.1 if it's a penny. And so we introduced a second way of doing estimates. In addition to maximum likelihood estimates, we're going to consider also in this course maximum a posteriori probability, or MAP, estimates. And the idea is actually very obvious. What we're really interested in is not the maximum likelihood, remember, was the argmax over theta of the probability of the data given theta. That's what we said was our definition of maximum likelihood estimate. But actually what we'd really like is, given the data, what's the probability distribution on theta? And fortunately, we already know about Bayes' rule. which tells us how to express the probability distribution over theta, given the data, in terms of these other quantities, one of which is precisely this data likelihood that we just were dealing with. And the other thing is what? Oh, wow, it's the prior on theta. So if I have a penny and you want to say, well, I'm going to put a prior distribution on the theta for your penny that's very close to 0.5 and doesn't have much probability for theta being far from 0.5, then Bayes' rule tells us how to combine your prior with the observed data to get the probability of the posterior probability on theta given the data. Now, of course, Bayes' rule also involves this denominator, but fortunately, if here what we want is the argmax over theta of that, then this thing is no dependency on theta. And so the argmax of this equals the argmax of just the numerator. All right? So method number 2, MAP estimates, maximum a posteriori probability estimates for theta. So how can we do that? Well, first, don't look at that. All right. First thing we've got to do is we've got to figure out how are we already know how to represent P of data given theta. That was on the previous slide. That's the arithmetic we were just doing, right? It's the product of all the probabilities of the individual coin flips given theta. We know that. But now if we're going to use this kind of map estimate, we have to make up some way of representing a prior probability over theta so that we can use Bayes' rule in this expression. Now, think about that for a minute. And let's think again of my penny, or this tack. When I look at this tack, I think it's going to come down on the point, maybe 0.2 with 0.2 probability, and most of the time it's going to end up like that, right? Not with a point not down. 0.8, I'm going to say. Well, that's kind of the most likely. I'm not really sure. But I'm guessing, if you ask me to pick a probability, I'd say, well, I'm going to say probably point up 0.8. It's an unfortunate ambiguity in the word point. And down 0.2. But actually, I'm not sure. So what I really want to say is there's some probability distribution over theta. It's not necessarily 0.8. It's with high probability to be 0.8, but also some probability that it's 0.75, some that it's 0.6. But I want to make it more probable that it's 8 than that it's 0.3. So I want a whole distribution over theta as my prior. And for reasons that will become very clear very soon, what we like to do is use what's called a beta distribution to do this. And here's the beta distribution. The horizontal axis here is our theta. Or I'm sorry, the horizontal axis here is, yes, theta. And the vertical axis here is the probability of theta taking on that value. Whoa. The probability of theta taking on that value. And so here's the prior distribution on theta I might give for my penny. Here's a different prior distribution I might give if I want to say that, I want to put the maximum on the probability that theta is 0.3. Or here's a different one I might use if I'm even more sure that it ought to be in a particular place. Well, the functional form for this beta distribution is this. And what we're looking at here are just curves that plot that out. But I want to draw your attention to this functional form. Does it look familiar to you? It should. The numerator there is just like the expression we wrote down for the probability of the sequence of 5 flips. Right? It's theta to some exponent, which is, in our case, was the number of times we observed ahead, times 1 minus theta to some other exponent, which in our case was the number of times that we observed a tail. And so you can think of the beta distribution as essentially a prior that hallucinates some number of imagined head flips and tail flips, and that is our prior. And then the probability of theta is just proportional to how probable that value of theta would be if we observe BH minus 1 heads and BT minus 1 tails. There's a reason we choose this, because it's going to turn out to make the arithmetic of applying Bayes' rule trivial. So let's see how that works. It works very nicely, because now when we want to know, here's our prior on theta. We're interested in the argmax of this over theta of this, which, as we saw, the numerator of Bayes' rule is this. And so now that means we have to multiply our data likelihood, P of D given theta, which you recognize from before as just this quantity, times P of theta. So what happens when we do that? Well, we have, let's do P of D theta first. So we have that times 1 minus theta alpha t. And then that's our P of D given theta. And then our P of theta is just this thing. Well, if I multiply it by that, then I get a theta times a BH minus 1 times 1 minus theta times a beta tails minus 1 all over this, what's that thing on the bottom? You know, the thing on the bottom is just a normalization term to make sure that our prior P of theta integrates out to 1. We can only have a total probability of 1. So it's just really a normalization constant. But now that I've written it this form, you see how beautiful it is that we use this beta prior? Because now I can just combine these exponents. Basically, what I've got is theta of alpha h plus beta h minus 1 times 1 minus theta times alpha tails times plus beta tails minus 1, all over this normalization constant. So you see, when I go to maximize this with respect to theta, we've already done the arithmetic on that. This is just exactly the form of the expression we did our argmax on when we did our maximum likelihood estimate, remember? We had some number of observed heads, which in our case was alpha h, but now we also have these hallucinated beta h minus 1, effectively hallucinated heads that were built into, which are the beta parameters from our prior. And a certain number of probability of tails, we were taking that to an exponent which reflected the number of times that we observed tails, plus, in this case, a term from the prior which we can think of as a hallucinated number of tails. And so this is the expression we end up maximizing. And who can tell me what the argmax of this will be? Over theta the argmax of that over theta will be what? You got it. So it's just, it's like, it's as though we're pretending we observe this many heads and this many tails. It's the same form as we solved before. So it's as though we observed this many heads and the total number of flips we observed was the number of imagined plus truly observed heads and imagined plus truly observed tails. So the map estimate is, again, the fraction of things that turned out heads, but now our prior over theta, which came from that beta distribution, which had these convenient parameters. When we pick the prior, we essentially pick beta to reflect our prior. So if I think that my penny is likely to be have a theta somewhere near 0.5, I might do a beta with a beta distribution with this number equal to, let's say, 2, and this number equal to 2. They're equal if I think the penny is likely to come out 0.5. If it's a thumbtack that I think is likely to come up 0.8, then I might use beta heads of 8 and beta tails of 2. If I'm really confident, then instead of 8 and 2, I'll use 800 and 200. I'll hallucinate even more experimental outcomes in that proportion. Okay? So now you see the beauty of these distributions and the map estimate. So let me just flip to, here are some, as usual, extra slides. But and we've already answered this question. So I just want to make one point about this, which is what we've seen here is a lot of stuff in rapid fire as promised, but I hope a lot of it's review for you. Some of it won't be. But what we've seen is random variables, probability distributions, and then the key question of how do we estimate parameters for probability distributions. And we had two approaches that we talked about. One was maximum likelihood. Let's pick the value of theta, our parameter theta, that makes the observed data as probable as possible. Maximum likelihood. But we were a little nervous about that because we got the same estimate if we had only a small number of experiments as if we had a large number of experiments that happened to have the same proportion of heads. So the second approach was to actually use Bayes' rule and to put a prior on theta that reflected our prior assumption about what theta's value is likely to be. And we didn't have to commit to a single value. We put a whole distribution over theta. And then we fold that prior in using Bayes' rule with the observed data to get the posterior distribution, which is the probability of theta given the data. Now, the arithmetic worked out surprisingly conveniently for us, but that wasn't an accident. That was by design because the beta distribution is the conjugate prior for the binomial distribution. What do I mean by that? This slide says it all. So in the coin flip problem, our data likelihood, the probability of the data given theta, is just this expression. And our beta distribution, notice, had a very similar form. And so when we multiplied those together, we could just sum their exponents. And in fact, the posterior distribution, which is the product, of course, or proportional to the product of those two distributions, is itself a beta distribution, whose parameters are now our original betas from the priors plus the observed alphas for heads and tails. So a conjugate prior means a prior whose functional form is chosen to have the property that once we fold in the data, the posterior distribution on theta given the data is also the same form, in this case beta, as the prior was. And so conjugate distributions are a wonderful thing in terms of simplifying the math. And as we'll see, many of the conjugate distributions, even though the equations sometimes look scary, mostly because of the horrible-looking normalization terms that are in there, but intuitively, many of these priors that we put on parameters correspond to thinking about have the same effect as introducing hallucinated examples along with our observed data. Okay, so that was a lot to swallow in a day. come to the recitation and review this stuff. And next time we're going to talk about Bayesian classifiers and practical ones, and each of you will be a training example on Thursday, so come prepared.